Hello, students. Let's continue our discussion of differential equations, and we begin with an example. Find the general solution of this differential equation. It says 5y to the fourth times dy dx equals 2x. Now, what we did in the last lesson was we verified solutions, and then we also solved differential equations of this form. By integrating. Dy dx is some function of x. But you notice this differential equation is not of this form. We have this 5y to the fourth here. Well, let us integrate both sides with respect to x. I have an integral, 5y to the fourth, dy dx. And I am integrating with respect to x. Now, on the right-hand side, we have an integral of 2x dx. Very nice. Okay, remember that y is our function of x. So y is really a function of x. And if you look at the left-hand side, what do we see here? Well, it looks like something that we've studied very recently, and that is integration using substitution. So you notice that the left-hand side is just the integral of 5y to the fourth dy. And then I'll just recopy. Now, what does this say? Well, let's integrate the left with respect to y. In fact, I'll do this over here. We have y to the fifth. And over here, integrate with respect to x. Really, we're used to putting plus c on each side, but there's just one constant here. So y to the fifth is x squared plus c. Now we're trying to solve y as a function of x, and I can just take the fifth root here. So y itself will be the fifth root of x squared plus c. And here's my general solution. Let us check. This will be probably the only one, this video, I will verify. We did a lot of that last time. So let's check here. If we take dy dx, what do we have? Well, this is chain rule. We have 1/5. We have x squared plus c to the minus 4/5. And then times the derivative of the inside function, which is 2x. 5y to the fourth dy dx would be 5. This is x squared plus c. This is a 1/5 power, so y to the fourth is x squared plus c to the 4/5. And then, why don't I just put this in the denominator? We have a 5 x squared plus c to the 4/5. Right? Now, you notice this quantity is 1, and so we're left with 2x. Okay, this is, as I mentioned, the only one I will verify this video, but it is wonderful to practice. Okay, now this differential equation, which we just solved, and we also checked our answer, is an example of what's called a separable differential equation. So let's get to the definition of that right now. A separable differential equation is one of the following form. We have dy dx. It's some function of x divided by some function of y. Now, let's look back at our example to make sense of why this fits the definition. In our example, we had the following. We had dy dx equals, let's scroll back. It would be 2x divided by 5y to the fourth. So 2x divided by 5y to the fourth. And you see, this exactly fits this definition. Now, how to solve? Well, really, you could go through the chain rule every time, but we can remember a shortcut. So from the chain rule, which is really where this comes from, what you want to do is multiply both sides by q of y. So we would have the integral of q of y dy, and this will equal the integral of p of x dx. So the way to think about it, as I said, it comes from the chain rule, is that you multiply both sides by q of y and multiply both sides by dx. But this is a differential, not exactly a fraction, but this is correct from the chain rule, as we saw in the last example. All right, then what? Well, we integrate capital Q of y equals capital P of x plus c. And this is where capital Q and capital P are antiderivatives. So maybe I should write this, where capital Q prime of y is little q of y, and capital P prime of x is little p of x. Okay. Then we can solve for y in terms of x. So this is how we solve separable differential equations. All right, so here's an example. Solve the initial value problem. Well, we practiced some initial value problems last time. Here we will not have some constant c in the end. We will have to use our initial conditions to solve for the c. Let's go. We have an integral. We have 3y squared dy equals the integral of cosine t dt. This was the separation of variables. Okay, y cubed equals, well, we integrate cosine, we get positive sine plus c, and now we can take the cube root. So y is the cube root of the sine of t plus c. Okay, we're not finished. We need to use our initial condition to solve for c. So let's do this down here. Y of 0 would be the cube root. The sine of 0, okay, 0 is right here. The sine of 0 is 0. So we have 0 plus c. We want this to equal 2. And now you can see our constant will be 8. So c equals 8. Now let's write our final answer. My function y is the cube root sine of t plus 8. Just as we did in the last one, you could check. You could calculate dy dt, and you will see that y satisfies this differential equation. You can also evaluate at 0, and you will get 2. Next example, we want to find the general solution to this differential equation. And so our final answer will have a constant here. Maybe before I start, let me just slightly rewrite this. We have dy dx equals e to the y times x squared. Okay, now I'm ready to solve. We have the integral. Well, when you divide both sides by e to the y, we have e to the minus y dy, and this will be equal to the integral of x squared dx. Well, e to the minus y, we integrate. We have minus e to the minus y. This will equal x cubed over 3 plus, let's see, I'll call this, say, C1 for reasons that will hopefully be clear momentarily. Now, I'm trying to solve for y. The first thing I would do is multiply through by this minus sign. So I have e to the minus y. This will be minus x cubed over 3. And then I would have minus C1, right? Yes, I would. But subtracting a constant, well, it's the same as adding a constant. It's just some constant. So I'm just going to put plus c here. Now, how do I get the y outside of the exponent, I want to take the natural log of both sides. So I'm going to have minus y is the natural log of c minus x cubed over 3. And one more step, we can just multiply through by -1. So y is minus ln of c minus x cubed over 3. This would be our final answer. Once again, with all of these, you could check. You could calculate y prime, divide by x squared, and you should have e to the y. Next question, solve the initial value problem. You notice that we will not have a constant here. We will have a particular solution. Now, what I want to do is divide by y squared, which is not a problem because y is not identically 0. Y of 0 is 1. So we can divide by y squared. We have an integral. I'll write it this way, y to the minus 2 dy, and this will be an integral of x dx. Power rule on both sides. So maybe I'll start over here. Right-hand side is x squared over 2 plus, maybe I'll call it c1. Again, you could call it c, it's just a constant. Now this side, the left-hand side, we would have y to the minus 1 over minus 1. This is just negative 1 over y. I have negative 1 over y. Now it's kind of similar to the last in that first we multiply through by a minus sign. 1 over y will be, say, c minus x squared over 2. But then to solve for y itself, there's a few things you could do. You could either multiply here, and then we would get 1 is c minus x squared over 2 times y, and then just divide by this. That would work. Or if 1 over y is this, y itself is 1 over here, c minus x squared over 2. Now, typically I don't leave fractions in the denominator, although there's nothing wrong with this. I probably would multiply through by 2 everywhere. Maybe I'll do that at the end. So y of 0 is, it's 1 over c. And this is supposed to be 1. And so you see the constant is just 1. So I get that y is 1 over 1 minus x squared over 2. This is where I was saying I typically don't leave fractions in the denominator, so multiply both the numerator and the denominator by 2, and it's a little bit nicer. We have 2 divided by 2 minus x squared. Okay. This is my final answer here. Let me take you back to the last lesson, last video. We verified. This was our basics of differential equations video. We verified that this function is a solution to this differential equation. You might recall. Well, let's find the general solution using separation of variables. Maybe before I begin, let's rewrite this. We have dy dx equals x over y. All right, so we have an integral. This will be y dy equals the integral of x dx. Oh, these are very nice functions to integrate. We have y squared over 2 is x squared over 2 plus c. Maybe I'll even write c1. It's fine. We could call it c or c1, as I mentioned before. Let's multiply through by 2. So we have y squared is x squared. It would be plus 2c1, but 2c1 is just some other constant, so I will call this plus c. Okay, how do we solve for y? Well, we can't just take the square root. Certainly we see square root of x squared plus c is a particular solution, but it could also be the negative square root. So if we solve for y, we get y is plus or minus the square root of x squared plus c. Certainly, what we verified is of this form. Now, this points to a remark. You see, sometimes we cannot easily solve for y as a function of x, and we can leave our answer with y implicitly defined. So, for example, this type of problem, our book would leave the answer as y squared is x squared plus c, rather than putting the plus or minus here. But let's do another example where it is not so straightforward to solve for y as a function of x. Right here, and we will leave our answer in implicit form. The first thing we can do is just rewrite this differential equation. We have 1 plus 2y squared dy dx equals y cosine x. I think that's good enough to get started. So we will have the integral of 1 plus 2y squared over y dy, and this will equal the integral cosine x dx. Well, the left-hand side is not substitution. We can just write this as a sum of two terms. So we have the integral of 1 over y plus, this will be 2y dy is the integral of cosine x dx. Now, integrate. We have ln, absolute value of y, plus y squared, equals this one. We have sine x plus c. Now you see, this is definitely not so straightforward to solve for y in terms of x. And so I will just leave this in implicit form. Okay, now I want to take you back also to the last video. And one of the very last questions I asked was, what is the general solution to y prime equals y? And I said, well, think about this for a moment. What's the only function that is its own derivative? And it's here, a constant times e to the x. This leads us into exponential growth and decay. You might have seen this in a pre-calculus course before, but I'm going to discuss this from the standpoint of differential equations. So a quantity, a of t, grows or decays exponentially provided the rate of change is proportional to the amount at that time. So this differential equation says the rate of change equals the amount at that time. Proportional, well, it says the following. It will say dA dt is a constant times A. This is the rate of change of the quantity is proportional to the amount at that time. If k is bigger than 0, this is exponential growth, and this is the growth constant. And if k is less than 0, this is exponential decay, and k is the decay constant. Now, the beautiful thing, we can solve this differential equation using separation of variables. So how are we going to do this here? Well, we would have the integral of 1 over a dA equals the integral of k dt. On the left-hand side, we have ln, absolute value of a. On the right-hand side, we have KT plus some constant, say C1. How do we solve for A? Well, we can take E to the on both sides. So here we get absolute value of A. On this side, we have E raised to the KT plus C1. And let me make a little simplification step, properties of exponents. This is E to the C1, E to the KT. What this says, just solving directly. First of all, we can think here, this part is always positive. It's E to something, but we get that A itself is plus or minus E to the C1, E to the KT. So this whole part, I'm just going to call some other constant. I'm going to have A as C, E to the KT. Now, technically, staring at this, we could get all possible positive and negative constants in C, but you notice that the constant solution, A equals 0, staring at this differential equation, is also a solution. And in this first step, I assumed A was not 0 to divide by it. So in a way, by putting any constant here, we've recovered this 0 solution. All right, here's my final answer. We have a constant times E to the KT. Now just a question and we can answer. What is the solution to the initial value problem? dA dt is Ka and A of 0 is some amount, A0. Well, we know it has this form. And then if you evaluate, we have the constant E to the 0, which is 1. This is supposed to be A0. And so you see we get the constant is this initial amount. So my answer is A of t equals A0 E to the KT. This is the answer here. This is the function that governs exponential growth when k is positive, exponential decay when k is negative. So let's do an example using this wonderful word problem. The amount, A of t, of sleep medication in the system t hours after dosing satisfies this differential equation. Wonderful. Assume the half-life is 2.5 hours and a patient takes 10 milligrams at bedtime. Then we have some questions. So maybe the first thing we can do is write out the formula for A of t. Okay, we know A of t will be 10 e to the kt. Now we have some information to solve for k. In particular, we know the half-life is 2.5 hours. Okay, so half-life, it says we have 5 milligrams left at time 2.5 hours. So we get this equation. 5 equals 10 e to the 2.5 times k. Now divide by 10, we get 1/2 is e to the 2.5 k. And we can take the natural log of both sides. ln of 1/2 is 2.5 k. Finally, solve for k. K equals ln of 1/2 divided by 2.5. And we will round this. This is approximately minus 0.2773. Now, let's go back and write our formula. A of t is therefore 10 e to the minus 0.2773 t. All right, I made the work for solving for k slightly smaller. Now we can jump into the problem. So, number 1, how much medication is in the system 8 hours after dosing? This is just A of 8. So we have 10 e to the minus 0.2773 times 8. And I will round again. 1.088 milligrams. Number 2, how fast, meaning at what rate, is the amount of the medication in the system decreasing 8 hours after dosing? So this is asking for A prime of 8. We know this is the constant, which is minus 0.2773 times A of 8. We have minus 0.3017. And this would be milligrams per hour. Last one, how much medication is in the system after a long time? Assume no redosing. This is a limit as t goes to infinity of A of t. This is what is asked here. Well, this would be a limit as t goes to infinity of this. E to the minus x looks more or less like this. So we have this negative exponent. This limit is 0. Fantastic. This was exponential decay. Now, let's do an example which is similar, but the differential equation will be a little bit more involved. So, a patient receives an initial injection of 60 milligrams of a medication. In addition, an IV is set to deliver 4 milligrams per hour. The body eliminates 10% of the medication present per hour. If y of x is the amount of the drug present after x hours, find a formula for y of x and how much medication is in the bloodstream after a long time. First, we need to write a differential equation here. So, dy dx equals every hour. 10% is eliminated, so this will be minus 0.1 y. That is a loss of 10% of the amount that you have in that hour, but then 4 milligrams are added, so plus 4. Here's my differential equation. Well, I can also write that y of 0 is 60. Okay, initial condition. Let's see, this is separable. I think to make the integration part easier, let me move this here. Let's factor out a negative 0.1. This is negative 0.1. And then we have y, this will be minus 40. And check, if you multiply this through, we have negative 0.1 y, and then we have plus 4. So this is great. Why did that help me? Well, now we can integrate 1 over y minus 40 dy. This equals an integral minus 0.1 dx. The reason I factored out this minus 0.1 is because now this is substitution, but my inside function has derivative 1. So I have ln, absolute value of y minus 40, equals negative 0.1x plus c1, or you can call it c. It's a constant. Now we can take e to the on both sides. So we have y minus 40 equals e to the minus 0.1x plus c1. This is e to the c1, e to the minus 0.1x. And very similar to when we solved the differential equation for exponential growth and decay, we will get y is a constant, e to the minus 0.1x plus 40. Now I can use my initial condition. So y of 0 is c, e to the 0 is 1 plus 40. This is supposed to equal 60. So I get that my constant is 20. Now I'm ready for number 1. We have our final answer. Y of x equals, we have 20 e to the minus 0.1x plus 40. Number 2, how much medication is in the system after a long time? Well, we want a limit as x goes to infinity of y of x. This is a limit as x goes to infinity of this expression. Very similar to the last one, this first term with the e to the minus in the exponent, e to the minus 0.1 times x, that term goes to 0. And so we are left with 40. This would be the amount of the medication present in the bloodstream after a long time if you stay hooked up to this IV. This is the end of this video. Thank you so much, students.